Hello, it's audio and video clear? Audio and video clear, beta? Everyone, please reply in the chat box. Audio and video clear? Please reply in the chat box. Okay. So, okay. Thank you for confirmation. So, find the final temperature inside the tank. Now, so first we have to we have to understand how to apply the conservation of energy for the unsteady flow problem. What is that, beta? See this one. So this is your supply line. Okay. First we have to draw a supply line. So this is your supply line. Okay. This is your supply line. Okay. This is your supply line in which the air is flowing. Now in the supply line, we have to connect a valve. We have to connect a valve. We have to connect a valve. Okay, we have to connect a valve. So this is your valve is beta. So this is your valve, connect to a valve. So this is your valve. We have to connect a valve is there. Okay, this is your valve. Okay, and this valve is further, this is your supply line. Okay, this is your supply line. And this is your pipe, which is connecting pipe, and in this one there is a tank. There is a tank is there. Okay, this is your tank. So in this one there is a tank. Okay, this is your tank. Okay, so this is your tank. Clear na? This is your tank. Now in this one there is air in the pipeline. Air, this is your air supply line. Supply line, this is your air supply line, and the property it is given, the initial pressure in the air, it is given how much it is? It is your 250 kilopascal. Okay, and initial temperature it is, that means initial, that means this I is inlet. Okay, this is your given 400 Kelvin, it is given. Okay, now in this one there is the air which is drawn, and this is your valve. This is your connecting valve, and this valve act as a throttling valve. Clear na? This valve act as a throttling valve, and we have to control the flow from this valve, and this is your tank. This is your valve. This is your valve, and this is your tank. And the tank, it is given the up to what level the tank will fill. The level is, that means the final pressure of the tank, it is reaches or equal to 250 kilopascal, and initially the mass of the tank M1 is equal to 0. Initial mass of the tank, it is 0. We have to find what is the final temperature of the air inside the tank. So my dear, here the notation is very important. Let's suppose this is your inlet section. Let's suppose this is your into the pipe. That means this is your inlet to the valve. This is your inlet to the valve beta. This is point I, inlet to the valve. There is no any exit. So these are the case of charging. Okay, these are the case of charging. So here there are 4 points I, that means section I, section exit, state, this state, it is for the control volume, state 1 and state 2. Now my dear, initially, that means initial state, it will at point 1, and after charging it will reaches at point 2. The tank, it will reaches at point 2. So this is your final state, this is your initial state of the tank. So initially the tank is evacuated, that means M1 is equal to 0. Okay. The final property of the tank, P2, it is given 250 kilopascal. We have to find what is the final temperature T2. Okay. Now the inlet property, it is given Pi is equal to 250 kilopascal, and inlet temperature, it is given 400 Kelvin, and there is no any exit. This is only charging, there is no any exit, so exit condition is 0. Okay, so this is the state section 1, inlet section, this is your exit section, this is your state point 1 of the system, and this is your final state point 2 of the system. Okay, now we have to apply two conservation equation. First we have to apply the conservation of mass. Conservation of mass. What is the conservation of mass? What is the conservation of mass? Mass at inlet section minus mass at exit section is equal to final mass of the system minus initial mass of the system. And this is for the system, and system, it is your control volume, open system. Now my dear, the initial mass of the system is 0. There is no any exit. That means the inlet mass is equal to final mass of the system. This is very clear. So this is equation number first, which is according to the conservation of mass. Now we have to apply the conservation of energy. So we have to apply the conservation of energy. Conservation of energy. Okay, conservation of energy, and this conservation of energy is according to the first law of thermodynamics. First law of thermodynamics. Okay, this is your first law of thermodynamics. What is the conservation of energy for the first law of thermodynamics? What is the conservation of energy, beta? We know that heat plus inlet mass Mi through the mass enthalpy V1 is Vi square by 2 plus Zi. Right, please write complete equation is equal to change in energy of the system M2 U2 plus V2 square by 2 plus GZ2 minus M1 U1 plus V1 square by 2 plus GZ1. So this is for the system. This is for the control volume plus exit mass into with the enthalpy HE VE square by 2 plus GZE plus work. So this is the conservation of energy in the case of steady flow. Now my dear, there is no mass initially, so M1 is 0. There is no any exit, it is 0. Okay, so these two quantity, it is 0. Now my dear, the tank is insulated, so this is also 0. There is no any working device installed with the tank, that means there is no any electrical heating. Oh, okay. Now it's okay. Okay, thank you. Now it's okay. Now Nikhil, it is okay, beta? Okay, so there is no any mass. Now we have to take, if it is not given, we have to take the change in kinetic and potential energy are negligible. That means we have to take change in kinetic potential negligible. So what is that beta? Mi Hi is equal to M2 U2. This is your according to conservation of energy. So this is your equation number first. Second, now according to the conservation of mass, what is that? M inlet mass is equal to final mass of the tank. So we have put here, so this will cancel out. Why? Because inlet mass. Now what is that beta? Inlet enthalpy is equal to final internal energy of the system. This is very important relation. This is very important relation. That means my dear, if this is your tank, okay, in this tank there is your inlet. Let's suppose this is your inlet. In this tank, this is your inlet I. So what is the enthalpy at inlet is equal to the final internal energy of the system. The condition it is given. When it is, so someone asks you the inlet enthalpy is equal to final internal energy of the system. When it is? When there is no change in kinetic and potential energy, no any heat transfer, no work transfer, okay, and initially it is evacuated. In that manner, the inlet enthalpy, what is the enthalpy which is in with the help of the air at the entry is equal to the final property of the tank in the for the air. That means we know that for the ideal gas, for perfect gas, what is that? Internal energy is equal to CVT, enthalpy is equal to CPT. We know this thing. Put here, so this is your H, so this is your what beta? Ti is equal to C, so this is your U, so this you can write like that, CP Ti is equal to CV T2. So what is T2 temperature? T2 is equal to Cp by Cv into Ti. And what is the, for the perfect gas, Cp by Cv is equal to gamma. That means adiabatic index. That means you have to write like that, ki sir, T2 is equal to gamma into Ti. This is very important relation. Now the problem is finished. Put the value of gamma 1.4 and put the Ti temperature. What is the Ti temperature it is given? 400. Multiply with that, you have an answer. So what is your answer? The answer is gamma is equal to 1.4 into 400. 1.4 into 400, and this is equal to how much it is? 560 Kelvin. Now my dear, there is one observation here. See, the problem is finished. So you just remember this relation. If you remember this relation, directly put the value, you have an answer. But this relation says something. That means if you have this tank, that means this is your tank, okay, this is your tank, okay, and in this tank there is a supply line. This is your supply line beta. This is your supply line in this tank. This is your supply line, okay, Okay, so what the enthalpy H here is the temperature which is at entry, and here is the temperature T2. Okay, na? And in this analysis, the T2 temperature must be greater than inlet temperature. So our one question is that, what is the question? This is our concept. What is the question is that, who is the responsible to increase the same fluid? That means, who is the responsible to increase the temperature of the air that presents inside the tank? That is my question. That means, what we have to write, where the energy to rise the temperature of air comes from that means, this is why. The question is why. Anyone beta? Why this temperature will increase? Anyone please reply in the chat box. If you are there, please reply in the chat. So why this temperature increase? See, my dear, what is your conclusion? The observation is, sir, Hi. That means, what is the final internal energy of the system is equal to inlet enthalpy. And what is the enthalpy, beta? Inlet internal energy plus P inlet into Vi, specific volume. Right? See very carefully. That means, inlet enthalpy is equal to, that means, what is the enthalpy is in to the container, in that energy, that means, this is the energy, enthalpy, it is a form of energy. So that energy, some part of the energy, it is converted into flow work, yeah, flow energy, yes or not? So this enthalpy, this is the internal energy, yes, the fluid is there, the internal energy is there. But along with the internal energy which is entering, along with that there is a flow energy will add. So this flow energy will be converted into the sensible energy, into the tank, and that sensible energy will be responsible to increase the temperature of the tank. Okay, that means, this is your internal energy and this is your flow work. This total energy, that means internal energy, flow work, converted into, that means this converted into, that means this is your total energy, internal energy entering plus flow work entering. This total energy is converted into the total energy of the tank. Total energy of the tank. This is your tank total energy. This is your tank total energy. Yes or not? Tank total energy. And this is your internal energy which is in through the supply line. And this is the flow work which is into the supply line. And this flow work will be responsible to increase. Why it is? Why? Because this is your R into T. And that temperature will extra added into this one. And that will increase the temperature of this system. This system temperature will increase. That means, the part of enthalpy, this is very important thing. The part of the enthalpy, the part of the enthalpy is the flow work. Okay, and this flow work and this flow work and this flow work converted into sensible energy, sensible energy, sensible energy, it increase the temperature, which is increase the temperature. That's it. So these are the interview question which is always asked in the interviewer. So why this temperature will increase? This temperature is increased due to these factors. This factor is responsible to increase the temperature of the system. Clear? So these are the things which I want to discuss with you. Why? Because many times you are stopped here, but you don't know why the system temperature will increase. Why? Because if you supply, that means you are adding something, the system internal energy will increase. But this system internal energy, who is responsible? So the responsible energy is, that means you are, see, if there is a fluid, there is an internal energy. But if you want to something in, so if you want to something in, there must be have to supply the flow work. So along with the internal energy, the extra component, that is the flow work, which is by default entry to the system. And that flow work is responsible to suit the temperature of the tank. Clear? Now we have to take the next problem. This is really very good problem is there. Please read this question, beta. Please read this question. Please read this question, beta. And please tell me on which chapter this question is related. Please tell me on which chapter. First decide. So what is that? A adiabatic vortex tube, that means there is no any heat transfer in there. As shown in figure, this is the T shape. Below, the supply with a 5 kg of air. Okay, 5 kg of air, that means mass flow rate it is given at the inlet. That means this is a section 0.1. This is the section 0.1 at inlet section. Let's suppose this is section 0.1. At inlet, this is the mass flow rate it is given now. And temperature it is given. At this temperature it is entering. To separate two separate stream of air are leaving the device from outlet 2 and outlet 3. So this is your outlet 2 and this is your outlet 3. Okay. So the fluid is coming here and it is splitted. Okay. So some part of the fluid which is entering at 0.1 will be going to the part 2, 3 and remaining is part 2. Right. Two separates of the air leaving the device from the outlet 2 and 3. So 2 and 3 is outlet and 1 is inlet. So 1 inlet, 2 exit. 1 inlet, 2 exit is there. Hot air leaves the device at a rate of 3 kg per second from the outlet 2. That means at this point there is a hot air. Okay, hot air. Okay, how much the mass flow rate? 3 kg per second. And what is the pressure? 100 kilopascal and temperature 340. Okay. While remaining, why? Because 5 kg is entering, 5 kg entering, here 2 kg, 3 kg in this side. So in this side there is a 2 kg. Yes or not? So 2 kg of the air which is cold. So what is the function of adiabatic vortex tube? It will separate the fluid and at one end there is a hot air and other end it is a cold air. Okay. Streaming leaving the device at this pressure 100 kilopascal and 240 Kelvin. Okay. So these are the situation it is given. Now consider a constant specific heat of the air. It is given Cp value it is given. The gas constant it is given. there is no any work transfer across the boundary of the system. That means if you design the boundary, this is our boundary. If you design, this is your control volume, that means control surface, there is no any work transfer is there. This is not any working device is there across the boundary of the device. The rate of entropy generation, you have to require the rate of entropy generation. So my dear, what is that? So we have to find the rate of entropy generation, okay. So simply this is your stream, yes or not? This is your stream, and in this stream, this will separate in this. One is in this direction, other is in this direction. So these are the stream separate. These are the vortex separator. Now this is at point. It is given. We have to select this one. This is your control volume. Okay, we have to take. This is our control volume. We have to take, this is our control volume, okay. This is our control volume. In this one, there is, this is your section 1, this is your section 2, I think, yes, 2, and this is your section 3, okay. Now, at point 1, it is given mass flow rate, it is given, how much it is? It is your 5 kg per second. Temperature at inlet, it is given how much? 300 Kelvin. It is given, beta. All that quantity it is given. At a pressure is 500 kilopascal. Okay. Now it is exit at point 3, 2, and that mass flow rate at 2 it is given. How much it is given? 3 kg per second. At a pressure P2 is equal to 100 kilopascal. And at a temperature T2, it is your 340 Kelvin. Now, it is 3. So, mass flow rate obviously at 3 in this side, 5 is entry, 3 in this side. So, obviously, this is 2 kg per second, and the same pressure P3, it is also 100 kilopascal, okay, and temperature is 240 Kelvin. This is a very good problem, is beta. This is a very good problem. Really, this is a very good problem in the entropy generation chapter, okay. Now, so during this situation, what is the entropy generation of the system? My dear, it is also given Cp 1005 joule per kg Kelvin, and R value it is given 287 joule per kg Kelvin. It is given, and also it is given there is an adiabatic, that means there is a no heat transfer and no work transfer. These all quantity are given in the question. No heat transfer and no work transfer, okay. Now, how to find this one, beta? How to find this one? Please tell me. So, we have to apply entropy balance. What is that? Entropy balance. What is that, beta? Entropy balance. So, entropy balance. Entropy balance. Entropy balance. So, in the thermodynamics, there are 4 balance equation. Number first, mass balance. Number second, energy balance. Number third, entropy balance. And number 4, exergy balance. Okay? So, here we have to find the entropy balance. What is the entropy balance, beta? Please tell me. We know that, see, what is the entropy balance? So, entropy balance, it is there, S inlet, entropy inlet, S exit plus S of generation is equal to ds by dt of a control voltage. This is your entropy balance. So, this is your entropy transfer, rate of entropy transfer. This is all our rate basis. So, these are the entropy transfer this is your entropy generation, and this is your entropy change of the system. Entropy change of the system. This is your entropy change of the system. Now, my dear, who is the responsible to transfer the entropy? Who is responsible to transfer the entropy? The responsible factor is heat and mass. That's it. What is the entropy generation? Entropy generation, it is not a system property. It gives the information that system is reversible or irreversible. That means it depends upon the path. It's depend upon the path of the system, whether it is follow the reversible process or irreversible process. Okay? So, these are the path function. Path function. Okay? Now, my dear, we have to find this entropy generation. We have to find it. We have to find this entropy generation. Now, the second question comes, how to apply this entropy balance equation? So, there is no any heat transfer. That means this is an adiabatic device. So, in this case, there is no any heat transfer. So, this is 0. So, only entropy will transfer due to the mass. Only entropy transfer in this situation is due to the mass. Okay? No heat. Why? Because in the question it is said that this is the adiabatic. So, entropy transfer due to the mass plus entropy generation is equal to change in entropy of the system. All are the rate basis. All are the rate basis. So, my dear, what is in? There is one inlet and 2 exit. So, one inlet due to the mass minus plus of 2 exit due to the mass transfer plus entropy generation is equal to rate of change of entropy of the system. So, how to write this equation? Please see this. How to write? So, what is that? A rate of entropy entry minus rate of entropy exit plus rate of entropy generation, and see this one in the question it is given adiabatic vortex supply. See this mass flow, what is the mass flow rate at entry? The same mass flow rate at exit. What is the mass flow rate inlet? The same mass flow rate exit. That means this is a steady device. This is your steady device. That means what is the mass is in? The same mass is exit. That means 5 kg mass is in, there is a 5 kg mass is exit. That means system is steady device. If the system is steady, there is no any change in the property of the system. That means, very important, this is 0. This is 0. Why? Because steady device. steady device. Yes or not? Steady device. Yes or not, beta? Okay. That means this is 0. Clear? Now, what is the entropy inlet? Inlet is M1, specific entropy at 1. This is your inlet at point 1 minus the exit is 2. That means M2 dot specific entropy at 2 plus M2 M dot 3 specific entropy at 3 plus entropy generation. This is 0. All are the rate basis. Okay, this is your rate basis. Okay, this is M dot, so it is a rate basis. Now, so what is the entropy generation? Rate of entropy generation. If you rearrange this one, this is your M2 mass flow rate at point 2 into S2 plus mass flow rate at 3 S3, okay, minus mass flow rate at 1 S1. So this is your the equation, required equation. This is your required equation. So these are the entropy balance. This is your entropy balance for this device. Now, M2 it is given, M3 it is given, M1 it is given, but the entropy, specific entropy, it is not given in this question. So our next task is how to find the entropy. Now, my dear, according to the conservation of mass, what is that? Conservation of mass. Conservation of mass. What is the conservation of mass? Mass flow rate at inlet minus mass flow rate at exit is equal to change of the mass with respect to time rate basis of a control volume. But this is 0. Why? Because steady flow. So what is the mass at inlet? 1 inlet is equal to mass at exit. What is the mass at inlet? M dot 1. What is the mass at exit? M dot 2 plus M dot 3. So this is according to the mass balance. Now from here M1 we have to put M2 and M3. M2 and M3. Okay. So S rate of entropy generation, if you arrange, then arrange is equal to mass flow rate at 2 S2 minus S1 plus mass flow rate at 3 S3 minus S1. If you put this value, this is your equation. Now, this is your required expression. Now, so this is your vertex tube. In the vertex tube, this is your exit from the left, entry, exit from the right, entry. This is the beauty. That means, if this your entry is there, beta, 1 second, I have to change the color. Okay. If this your entry is there, from this entry, this is your 1, this is your 2, and this is your 3. So, M2 S2 minus S1 plus M3 S1 S3 minus S1. These are the entropy generation. Be careful. So, 2 minus 1, 3 minus 1. So, 2 minus 1 multiply with M2 plus 3 minus 1 multiply with M3. So, that is your entropy generation. 2 minus 1 multiply with M2 plus 3 minus 1 multiply with M3. That is your entropy generation. Now, the next task is that how to find this change in entropy. Now, in this case, beta, there is air is there, na? air. Say air act as an ideal gas. So what is the entropy of an ideal, change in entropy of an ideal gas? We know that. Very good. We know that. We know that. What is know that? Change in entropy of an ideal gas, that means final entropy minus initial entropy is equal to Cp. Why? Because this is a specific beta. These all are the specific. Okay, these all are the specific. So what is the specific? Specific entropy is equal to total entropy divided by mass. So if you write a specific, don't multiply with the mass. If you write total, then we have to multiply with mass. So Cp ln T final by T initial minus R ln P final by P initial. This we have. This is known for an ideal gas. Now, so S generation, this is equal to, now this is your 2 minus 1. So this is your 2, this is your 1, this is your 3. So 2 minus 1. So this is 2 minus 1, that means M2. M dot 2. 2 minus 1. So we have to write here Cp ln T2 by T1 minus R ln P2 by P1. So my dear, this is your equal to, this is what? This is what? This is your S2 minus S1. S2 minus S1. Now we have to write minus of S3 minus S1. So M dot 3 S3 minus S1. So Cp ln T3 by T1 minus R ln P3 by P1. Clear na? And this is your S3 minus S1. Put all this value, M2 is there, temperature is there, all the value it is there. All the value it is there, beta. Cp is there, R is there, P2 is there, P1 is there, T2 is there, T1 is there, Cp is there, T3, T1, all are the properties are given. Put and calculate very carefully. If you put all this value, the answer is 2.24 kilowatt per Kelvin. Kilowatt per Kelvin. This is your entropy generation. And my dear, this generation is greater than 0. That means irreversible process. Irreversible process. If it is 0, then in that case the process is reversible. If it is less than 0, process is not happening. The process is not happening. Clear na? So from that entropy generation, we have to identify also whether the process is reversible or irreversible, or the process is happened or not. So my dear, if the entropy generation is greater than 0, see this is positive, 2.24, it is a positive. That means this is an irreversible process. If anyhow, if the entropy generation final result is equal to 0, in that case the process is reversible. At any cases, if this generation is less than 0, process doesn't take place. So someone asks you whether the process in this situation, that means this is your situation, that means adiabatic vortex tube, in this situation, this process is happened or not. And also check if it is happened, so there is a reversible process or not. So yes, why? Because entropy is not equal to, entropy is not less than 0. Entropy generation is not less than 0. Entropy generation is not less than 0. That means the process is must be happened, number first. Now, number second, the entropy, if it is greater than 0, there must be a irreversible process. If at anyhow, if the entropy by default, if it is 0, the process is reversible. In that manner, you have to find. So this is very good question. Now we have to take the next problem. Okay, this one. These are the next question, and this question is applied thermodynamics, that means power plant. What is that? Consider a steam power plant operating on an ideal reheat Rankine cycle. That means there is a reheating. Okay. The work input to the pump, so there is a pump is there, 20 kilojoule per kg. The work output from the high pressure is 750. The work output from the low pressure turbine is 1500. The thermal efficiency, overall thermal efficiency is 50%. The enthalpy of saturated liquid and saturated vapor at the condenser pressure, finally it will reduce the pressure at a condenser pressure, and condenser is a negative pressure. And this is your saturated liquid enthalpy, and this is your saturated vapor enthalpy. The quality of the steam at the exit of low pressure turbine. That means you have to find the dryness fraction. You have to find the dryness fraction. So first we have to discuss what is the reheat. Okay. So see this one. This is your reheat cycle. Okay. This is your reheat cycle. What is the component there? This is your boiler. In the boiler, the high pressure and high temperature steam will be entering into the turbine, first turbine, and that turbine is called the high pressure turbine, where the work is out from this one. Work is out from this one. So this is your work output from the high pressure turbine, and this is the and then the again the steam is going to the reheat. So this is your reheater. It will again heat and come out to be the and entry into the low pressure turbine. This is your low pressure turbine, in which the work is out. That means work output from low pressure turbine. Now it will go to the condenser. From that condenser, heat will lose, and then again it is pumped to the boiler. So what is the function of reheat? You have to again heat after the expansion of the first high pressure turbine. Again you have to heat, and again you have to enter to the low pressure turbine. So what is the advantage of reheat? During the reheat, the quality of the steam will improve. The quality of the steam will improve. So this is your TS diagram in which the quality of the steam. See, initially if there is a no reheat, steam will expand and it will come into 6 dash. Now if we reheat, this is your reheat. This is your reheat. This is your reheat. So again you have to reheat, the quality of the steam will improve. That means the dryness fraction will increase. So what is the dryness fraction at this point? They are asking. What is the dryness fraction? So how to find the dryness fraction of this one? So my dear, so this is your ideal, we have to draw this one. Okay. So, one second. This is your T and S diagram, temperature and entropy diagram. So this is your T and S diagram, okay? This is your T and S diagram, okay beta? Now this is your saturation curve. This is your saturation curve. This is your saturation curve. So this is your temperature and entropy diagram. And this is your saturation curve. Now this is your boiler pressure. This is your boiler pressure and this is your condenser pressure. Okay. So this is your boiler pressure. Steam will enter. This is the point. Let's suppose this is your point number 1. Okay. At this point, this is the entry to the high pressure turbine. Sorry, high pressure turbine, and it will expand. Let's suppose it will expand up to point number 2, and again it will reheat. So if it will reheat, let's suppose it will reheat, and again it is entry to this point. So this is 2, 3, again it is expansion, 4, 5, and then it will pump at 6. So in this one, my dear, in this case, in this one there is a heat supply. In this one there is a heat supply into the boiler, and in this one there is also heat supply in the reheater. So 2 to 3 is the process where it is 2 to 3 in the reheater. 2 to 3. Okay. So let's suppose this is reheater. This is 2 to 3. So 2 to 3 is the reheater. Okay. So now we have to find the dryness fraction. That means we have to find X4. How to find? This is the output. 1 to 2 is the high pressure turbine. 2 to 3 is the expansion in low pressure turbine. So what is the net work in this case? Net work is the output minus input. So what is the output? Work output from the high pressure turbine plus work output from the low pressure turbine minus work input to the pump. Yes or not? Here we have to add the work. Why? Because 3 to 5 to 6 is the pump. Put all this value, you have a value. High pressure 750, low pressure I think this is your 1500, and the pump it is given 20. How much it is, beta? This is your 2230 kilojoule per kg. So this is a specific work, net specific work into the turbine. Now, what is the, we know that, what is this efficiency? W net by heat supply. And this efficiency it is given. How much the efficiency it is given, beta? 50%. So this is 0.5 is equal to W net we have 2230 divided by heat supply. So how much you have to heat supply? How much heat supply? It is your 4460 kilojoule per kg. That means this is a total heat supply. This is total heat supply. That means heat supply in the boiler and plus heat supply in the reheater. So total heat supply. That means 6 to 1 plus 2 to 3. So this is a total heat supply. Now in this one there is a heat rejection in the condenser. So what is the heat rejection, beta? We know that efficiency is equal to W net, that means heat supply minus heat rejection divided by heat supply. So this is your 1 minus heat rejection by heat supply. Now my dear, the efficiency is 0.5 is equal to 1 minus, what is the heat rejection? You have to find it. QR by Q supply. Q supply how much? 444460. So from here you can easily find what is the heat rejection. So how much heat will reject? Please tell me. The heat rejection is 2230 kilojoule per kg. Now my dear, that means this much of amount of heat will reject by the condenser. And what is the heat rejection by the condenser? H4 minus H5. We apply the H4 minus H5. So this is your TS diagram. Okay. This is your expansion. This is your expansion. Okay. So this is your 4. This is your 5. This is your 4 and 5. And steam it is there. Let's suppose this is your 4. This is your 4. Steam will entry at the point 4 into the condenser, exit at point 5. And this point 5, it is your Hg, and this point, it is your Hf. Sorry, this is your Hf, and this is your Hg, and this is your heat rejection. Okay. So heat, this is your heat rejection. So you can easily find heat rejection, it is your H4 higher enthalpy minus lower enthalpy H5. Okay. And this is how much? 2230, yes or not, kilojoule per kg. Okay, na? Now, what is H5? So, H4 minus what is H5 beta? HF. And this is equal to 2230. And we have, so H5. So, H4 is equal to, we have H5, HF. See this one? We have the enthalpy of the saturated liquid and enthalpy of the saturated vapor. That means 2600 it is there. So this is your 2600. This is your 2600. So if you done the calculation, this is your 2430 kilojoule per kg. Now my dear, you have enthalpy at this point, H4. So if you have enthalpy at wet region, how to write? HF plus X4 Hg minus HF. Yes or not? So indirectly, this is your HF plus X4 Hg minus HF. Yes or not? So you have HF, you have Hg, you have HF. All this value you have. All this value you have. So from here, you can easily calculate the dryness fraction at 0.4, and this is approximately 93%. Clear? So today, we have to discuss about 2 questions of the basic thermodynamics and 1 question of the power plant. Okay? So I hope you have got something from here. Be careful for the calculation in the gate part. Okay? So now in the next session, why? Because this is only 1 hour session. So in the next session, we have to discuss about the PYQ of 2021. So this all are question of 2021. Now we have to discuss 2020. So in the 2020, there is a very good question is there also. So I hope you are like this video. Thank you.